Our next speaker is Andrea. He is just finishing his first year in Pavia in a joint program with Lugano. And I do not write down the title.
Good afternoon, everybody. As Mickey said, my name is Andrea Medaglia, and I'm a PhD student at the University of Pavia. And today I would like to talk about a novel numerical approach to uncertainty quantification in multi-agent systems. So, in the first part, I will talk about the Boltzmann Equation, and then I will introduce kinetic models or multi-agent systems. Then I will introduce in this kind of models the uncertainty quantification, and in the end I will talk about the numerical approaches to uncertainty quantification and this novel approach recently introduced by my advisor, Mathematicians from the University of Pavia and other researchers. So let's start from the very beginning of the story. In 1872, Boltzmann introduced this famous equation that described a system of n interacting particles from a mesoscopic point of view. Microscopically speaking, this kind of system is described by a Newton equation. Okay. No. Qual è il due? Okay, microscopically speaking, a system of n particles is described by n coupled Newton equations, but the number of the particles is so high, of the order 10 to the power of 20, and it is obviously not feasible both from a numerical and analytical point of view. So the idea of Boltzmann is to describe this system from a mesoscopic point of view, that is, in terms of the probability density function, f, that is a function of the space x, the velocity v, and the time t. The physical sense of this object is that at fixed time, t greater than 0, if we integrate in a phase space volume this function, it gives the probability that one particle, but we don't know which particle, is in that phase space volume. And then, from this mesoscopic approach, we can recover the macroscopic observable quantities by means of the momenta of this distribution. So, this is the Boltzmann equation, and this term is the so-called transport term, but in the following, we will consider only the one-dimensional and space-homogeneous scenario, so this is equal to 0, and f depends only on v, that is one-dimensional. The last term is the so-called collisional term. It is an integral operator, and where epsilon is the so-called Knudsen number, and it is linked to the free path between one collision and another. And Q contains all the information on how the particles interact with each other. But before talking about the collisional operator, I have to comment two of the assumptions of the Boltzmann equation. I don't want to give the formal proof, but I think that these two assumptions are very important in understanding the form of this operator. So the first one is that the collision between more than two particles are disregarded. So the binary interaction are the only responsible for the variation of the probability density function in time. And the second one is the so-called molecular chaos hypothesis, or the Boltzmann ansatz. And it says that particles that are about to collide are statistically independent, as if they are randomly chosen. The idea is that after a collision, two particles are correlated, but before they collide again, they will undergo a number of collisions such that their correlation goes to 0. So the idea is that two particles are, let's say, always independent. This is the most general form of the collisional term. It is an integral operator where B is the so-called interaction kernel and can be seen as a sort of probability, or let's say a frequency of interaction. And in this term, we can see, let's say, a gain and a loss part. The gain part depends on the so-called post-interactional velocities, and the loss part depends on the pre-interaction velocities. So the idea is that a binary interaction maps the pre-interaction velocities into the post-interaction ones. So here I give you one of the most famous references for the Boltzmann equation by Carlo. And now we go to the, let's say, kinetic or multi-agent systems. About from the 50s, many researchers understand that there exist in, let's say, real life, many systems that show analogies with the, let's say, rarefied gas dynamics, such as the self-organized behavior at the macroscopic level and other features. So the idea is to identify the, let's say, agents with the particles, and with agents I mean, for example, cars in traffic flow, and I will use this as a working example. We can, or let's say, birds in flocking models, tumor mass in tumor growth model, and so on. And the idea, as in the Boltzmann equation, is to recover the observable quantities, the macroscopic quantities, with the momenta of the probability density function. And here I give you another nice reference for this kind of multi-agent systems that are systems composed by many interacting and indistinguishable, let's say, agents. So now I introduce a very simple model for traffic flow that is one-dimensional and space homogeneous. We define the velocity in the interval 0, 1 because we think that the velocity is normalized by the maximum value. And as before, we have to define the kernel and then the rule for the binary interaction. So we can choose two types of kernel, the so-called Maxwellian kernel and the so-called non-Maxwellian kernel that depend on the relative velocity of two, let's say, car or particles, is the same. And this is the binary interaction we choose, in which we have two particles, the so-called leader, that is the leading one, that does not change its velocity because of what happened behind it, and the follower, that is that changes its velocity with this rule, in which gamma is a proportionality constant, eta is a centered random variable that models the stochastic fluctuation due to the decisional process. Obviously, cars are no particles, so there is also a decisional process behind him. D is a diffusion coefficient, and E is the so-called interaction function that depends also on this P rho, where rho is the density of the cars in the street. P is the probability of acceleration, and E is this function. The idea is that when rho is near 0 in a free flow regime, this term is near 1, so this is almost 0, and the follower approaches the velocity 1, the maximum velocity. In a density traffic regime, where rho is near 1, this term is almost 0, and the follower had to adapt its velocity according to the velocity of the leader. The idea is then to construct a so-called Boltzmann type equation, that is the Boltzmann equation for the time evolution of the expectation of, let's say, a test function phi, that we think that phi is smooth and is a function of the velocity. And this is exactly the Boltzmann equation, not for f, but for the expectation of phi with respect to f. Where again epsilon is the Knudsen number, and these brackets are the expectation with respect to the distribution of eta. If we choose phi equal to v, we can study the let's say the mean velocity, the mean macroscopic velocity, and this is for a Maxwellian kernel. It is solvable, this equation, and we recover the so-called traffic diagrams that are well-known rule empirically and also experimentally. So we can see as this relation as a sort of validation of our model. But the Boltzmann equation is, in general, and also the Boltzmann type equation, is not suitable for study the asymptotic trend, because it is an integral differential equation, so it's very difficult. But fortunately, Cédric Villani in 1998 proved that in the so-called grazing or quasi-invariant interaction limit, conditional operator of the Boltzmann type can, let's say, goes to a collisional operator of the Fokker-Planck type. This limit is, the idea of the limit is that every binary interaction contributes little to the variation of the probability density function, but they are quite frequent in time. So the idea is that in the Boltzmann type equation, we set gamma equal to epsilon and the variance of eta, that is a centered uniform random variable that is proportional to eta, and then we let eta goes to 0. Eta is the Knudsen number, and it is linked to the mean free path between one collision and another. So if eta goes to 0, the collisions are frequent. But if gamma and the variance of eta is smaller, as we can see from this relation, V prime is near V. So the collisions are quasi-invariant in that sense. We can expand phi, we think that phi is smooth, and we can expand it over in Taylor series up to order 3. And we get this relation in which we define the term rest containing all the terms of order epsilon that vanish in the limit. And the other terms are the terms that survive in the limit. And then, integrating back by parts, these two terms, letting eta goes to 0, so this term is 0, and invoking the arbitrariness of phi, that is a test function, we find a wave form for the Fokker-Planck equation. So we can say that in Monte systems, when this limit is, let's say, is true, we can use both the Fokker-Planck and the Boltzmann equation. But as I said before, the Boltzmann equation is an integral partial differential equation, so it's not an easy task to study the asymptotic trend. And then we have to go to the numerical point of view. One of the, I think, the most used approach to the Boltzmann equation is the so-called direct simulation Monte Carlo. And it consists in performing the evolution of a finite set of particles or agents, because we have to think that in this frame framework, agents and particles are the same thing, by moving them according to their velocities and by operating collisions between randomly chosen particles. So we have to manipulate the so-called collisional term, inserting an upper bound for the kernel, capital sigma, in order to find a gain and a loss part, because then we can discretize the time domain and apply forward Euler scheme to the Boltzmann equation with this gain and this loss term. And to this equation, we can apply a simple probabilistic approach, that is that if this term is minor or equal to 1, we can say that with this probability, one particle does not collide because it does not contribute to the variation of Fn, that is f evaluated at time n. And with the complementary probability, the particle collides and it contributes to the variation in time of the probability density function with this, let's say, with this rule. Again, to this term, we can apply another probabilistic interpretation because B is always minor or equal to capital sigma, that is an upper bound for the kernel. And we can say that with this probability, a particle collides, because this is the term that contributes to the variation in time of the probability density function, and with the complementary probability, it does not collide. So, in more detail, this is the direct simulation Monte Carlo, as introduced by Nangu and Babowski. And the idea is that we have to sample the initial distribution, computing n initial velocities, then we discretize the time domain, and for every time step, we compute the upper bound for the interaction kernel. We set the number of collisional pairs, and then we check that if the sigma times xc, where xc is a uniform random variable in the interval 0, 1, is minor or equal to the relative kernel, and if so, we do the collision and we update the velocities. If not, we don't update the velocities. Here I show you some results of the, let's say, accordance between the analytical Fokker-Planck solution in a solid black line and the numerical solution of the direct simulation Monte Carlo of the Boltzmann equation for different values of the traffic density, and also for epsilon that, let's say, numerically goes to 0, and we can say that the more epsilon decreases, so in the quasi-invariant interaction limit, the more the two lines overlap, in the sense that the more the Boltzmann equation is similar to the Fokker-Planck equation. And now we move to the second part. This kind of multi-agent systems have to face the problem that we don't have a complete information of the system parameters or on the initial data. So the idea is that we have to insert in the model let's say the parameters as random variables distributed in a certain way, and then we have to quantify how much this uncertainty in the parameters of the system affects the results. One of the choices we can make on the traffic model is to consider the probability of acceleration, independence of zeta 1 distributed as P1, and the interaction kernel with an exponent zeta 2 distributed as P2, because it makes sense, because this is linked to the capability of the road, and we don't know the capability of the road, and this is linked to how the cars, the And if we want to apply a Monte Carlo approach to, let's say, this traffic model with two independent uncertainties, in principle, we have to sample the distribution of the parameters, let's say M1 and M2 times. So we have M1 times M2 combination of the parameter zeta1 and zeta2, and then we have to repeat the direct simulation Monte Carlo M1 times M2 times. Roughly speaking, this is not formal, but just to give you the idea, the error we are making is of order 1 divided by the square root of n, where n is the number of the sampling of the velocities of the direct simulation Monte Carlo, plus 1 to the divided by square root of m1, plus 1 divided by square root of m2. So if we want to balance this error, we need, in a sense, that n, m1 and m2 are of the same order. But if we want also an acceptable error, we need n, m1 and m2, let's say 10 to the power of, I don't know, 5 or 6 or even more. So this is the so-called curse of dimensionality, because as you can imagine, from a numerical point of view, this is a nightmare. So we have to handle this problem with another numerical approaches. This is the bad thing of the Monte Carlo approach. It is the curse of dimensionality. Obviously, it has also, let's say, good thing, because it is non-intrusive, since we don't have to change the code every time we update the probability of the law of the random parameters, and it is easy to parallelize, and most of all, it preserves the structural properties of the model, such as the positivity of the solution. Another numerical approach is the so-called stochastic approach. I will tell you in a minute what it is, but let me say just that it has bad things, because it is intrusive and problem dependent, and it may lead to the loss of physical properties, such as the positivity of the solution. But the good thing is that the stochastic approach has a spectral convergence in the random parameter space. And then I just put here a reference for the so-called multi-fidelity method, but I will not talk about multi-fidelity methods. This is a good reference if you want to understand more on this kind of methods. So let's talk about the stochastic approach. It is based on the polynomial approximation of the solution based on a set of hierarchical polynomials orthonormal with respect to the distribution of the parameters, following the so-called Wiener-Raschke scheme that simply says that if we have parameters distributed as, let's say, a Gaussian, the right choice for the polynomial is the Hermite polynomial, and so on. The idea, this is the orthonormality of the polynomial. This is the set of the polynomial truncated at the order capital M. The integral over the sample space of this polynomial is equal to 1 if k is equal to h, so if they are of the same order, and 0 otherwise. So the idea is to suppose that the probability density function solving the Fokker-Planck equation is smooth. Let's say we ask that it is in the weighted L2 space. We have to think that this weight is the law of the random parameters. So we can expand it over the orthogonal polynomial base, in the sense that we substitute f with fm, that is the sum over k from 0 to capital M of the at fk, that are the coefficient of the expansion multiplied by the polynomial of order k, and we sum it from k, for k from 0 to capital M. This is the coefficient of the expansion. It's the projection of the solution over the space generated by this polynomial. And the idea is that this object does not depend on the parameter z. The only dependence of the parameter is here. This is exactly the point, because we substitute the Fm into the Fokker-Planck equation. Let's say this simple Fokker-Planck equation with the drift and diffusion coefficient that does not depend on the random parameter. And then we project against capital Psi h for every h from 0 to capital M, and we exploit the orthonormality of the polynomials. The idea is that in this sum, only the term with h equal to k survives. So we get m plus 1 deterministic, let's say, Fokker-Planck equation for the coefficient of the solution. Because in this Fokker-Planck equation, there is no random parameter. And then we can recover the let's say, real solution by reconstructing in this way the Fm. Okay, the point is, what have we gained? Because now we have to solve n plus 1 equation with, I don't know, a finite element method or other method. What have we gained? That m can be relatively small. And this is the so-called spectral conditions. So let me sketch what does it mean. We take a weighted Sobolev space where, again, the weight is, in a sense, the low of the random parameter. And we can prove that for every function in this space, there exists a constant c independent of m, where m is the order of truncation, such that the error we make with this approximation is upper bounded by c divided by m to the power of r. So, roughly speaking, we can say that the more the probability density function f is differentiable, the more r is I, and the more the convergence with respect to m increases. And in particular, if the function is analytic, we have exponential convergence. So here I show you two examples taken from the book of Dong-Bing-Skew, Numerical Methods for Stochastic Computation, a Spectral Method Approach. I don't know if you can see, but this is a cosine, and it is analytic, and we can say that with an m of order, let's say 20, we recover the machine error, 10 to the power of minus 15. And here we have, I think, the absolute value of x, and with an expansion of the order, this is 100, we don't have a good error. This is the idea. This is another example taken from the traffic model with only one uncertainty in the probability of interaction. If we suppose that z is distributed uniformly, we can expand it over the Legendre polynomial base, and we can see that this is the error of the f at the final time. We can see that with a relatively small order of expansion, let's say m almost 40, we reach the machine error 10 to the power of minus 15. And this is exactly the idea. But as I said before, the stochastic hierarchy method has also a bad thing, because it is intrusive, and most of all, it may lead to the loss of physical properties. So the idea of my advisor, Mattia Zanella, Lorenzo Paeschi, and other researchers is to combine these two kinds of methods, trying to exploit their good thing. And the idea is to exploit the structural properties of the Monte Carlo and the spectral convergence of the stochastic galerkin. So let's start from the traffic model with two uncertainties. The idea is to take a set of velocities, where n, capital N, is the number of the particles, or let's say k, we have sampled, and to expand it over the Legendre polynomial basis. The two random parameters are independent, so we have the approximation of the velocity over this expansion is this double summation over h and k, and this is the projection of the velocity over the space generated by the two polynomials, as before. The set of polynomials are orthonormal, as I said before, so we can substitute into the binary interaction rule this approximation. But before doing this, we modify the binary interaction rule, inserting this indicator function. It simply tells us that if this is minor to this, the indicator function is 1, otherwise it is 0. We insert this kind of function because of this procedure of the direct simulation Monte Carlo that I showed before. And then we substitute the polynomial approximation and we project, again, as before. And in the end, we find this new binary interaction rule for the projection at V and at W that is deterministic. I have defined also the so-called collisional matrix, but it does not depend on the random parameter, and this is exactly the point. Now I have I and j from 1 to n divided by 2 because I have the couple, and h and k goes from 0 to m1 and m2 respectively, that are the maximum order of truncation. So the idea is that now we can apply the direct simulation Monte Carlo to this new binary interaction that does not depend on the random parameter, and we have to repeat the direct simulation Monte Carlo a number of m1 times m2, but m1 and m2 can be small and not at the same order of n as before. So this is the hybrid approach, the so-called direct simulation Monte Carlo stochastic galerkin approach. So the idea is to sample the initial distribution and then to compute the expansion vi m1 and m2 at the initial time, and then we get the coefficient at v, and then for every time step we do exactly the same thing we are doing before, the so-called direct simulation Monte Carlo, but as I said, not on the real velocity, but on the coefficient of the expansion of the velocity. And these are the results in the so-called one-dimensional convergence. The idea is that we fix one of the two random parameters and we compute the convergence with respect to the other, and then vice versa. So on the left, you can see the convergence with respect to the first parameter. So we fix the second, and we said that zeta2 is equal to 0. So this indicator function is always equal to 1. And then we consider zeta1 in the uniformly distributed in this interval. As we can see, for two different values of the density, we recover the machine error with a small expansion, 10, 20, or 25, let's say. On the right, we can see let's say, opposite cases. So we fix zeta1 equal to 2, and we let zeta2 two uniformly distributed in this interval, and now this indicator function is non-trivial, and the indicator function is not an arbitrary function. So we see that we cannot reach the machine error because the indicator function is not regular. And this is exactly the point of the stochastic approach, because it depends on the regularity of the function, on the regularity of, let's say, the problem. Okay, this is the two-dimensional convergence, and as we can see, the convergence with respect to the first parameter is, let's say, covered from the second one, and we can reach only 10 to the power of minus 4 for this plateau. But we can fix this problem with the so-called regularization of the kernel. So in order to have a good convergence, also with respect to the second parameter, we can substitute the indicator function with a sigmoid that is smooth and let's say a hyperbolic tangent, and it depends on this parameter beta, in the sense that the more beta increases, the more the sigmoid is similar to the indicator function. And this is the numerical results, and we can see that the smaller beta, the smoother, let's say the smoother is the sigmoid, and the better is the convergence, because the stochastic Galerkin part of this approach is sensitive to this thing. But the problem with this regularization is that we are no longer simulating the system, the same system, because the sigmoid is not an indicator function, and we can see from the time evolution of the energy, that is the second moment of the distribution. As we can see, if beta is let's say is great, so if the hyperbolic tangent is similar to the indicator function, the time evolution of the energy is quite the same. And if beta is small, we can see that the energy is different from the, let's say, real energy. So we have to take care of this problem, because we can have a good convergence, but we are simulating another system, another model. And the idea is that we can insert a sort of thermalization, imposing that at every time step, let's say the first two momenta of the distribution can have the right value, and in this way we can, roughly speaking, we can have a good convergence and the right value of the momenta. And here we can see the accordance of the time evolution of the energy with respect to the time with this new process that I call thermalization. And with this thermalization, as I said, we have the structural properties of the system, and we have the spectral convergence, because we reach the machine error with a small expansion. And this is exactly the strength point of this new approach that is called the direct simulation Monte Carlo stochastic Galerkin. So I conclude with this this scheme. So I introduced the uncertainty quantification for kinetic equations or multi-agent systems, and I explained the most used numerical schemes, trying to highlight the strength and the weaknesses of these approaches. And then I introduced this novel approach that is called direct simulation Monte Carlo stochastic Galerkin, with the problem of the regularization and the thermalization process. Thank you.
Okay, let's start with Nikos.
Thank you very much for the talk. Can you give some insight on how this thermalization works? So, for instance, I would have expected, let's say, an error depending on your beta. So, does thermalizing kind of get you an exact indicator or something like that? So, how does it?
Okay, the point is that the thermalization is based on the Fokker-Planck equation. So, in the Fokker-Planck equation, the indicator function does not converge because the indicator function is due to the direct simulation Monte Carlo. It compares because we have to make this selection at this point. We have to make this selection, so we insert here the indicator function. But if we make the grazing or quasi-invariant interaction limit, we recover a Fokker-Planck, and in the Fokker-Planck there is no indicator function. So from the Fokker-Planck we have, let's say, the right value of the energy, and the energy does not depend in that case. Does not depend on this.
Please, any other question from the floor? Okay, so maybe first Alan.
I have a question regarding the approximation results. You've talked about some error estimates for stochastic hierarchy methods. Do you have reached anyone for the new combination of stochastic hierarchy and Monte Carlo? Or you are expecting exactly the same convergences rates? You told, if you go previously again,
Okay.
in the first part, you were talking about some error convergence that goes down as the number of numerical equations you are solving times the order.
Here.
Yeah, exactly. This on the lower right.
Okay.
Are you expecting
Here.
something like that for your methods too, or
Yeah.
you've proven something?
From a, let's say, analytical point of view.
Yes.
Or from
Yes. Analytically and numerically.
Analytically, the point yes, the answer is yes. I expect this kind of convergence, but the problem is that the convergence is problem dependent. It depends on that. So, from a theoretical, let's say theoretical point of view, if I insert this kind of uncertainty, I expect that I have a good convergence because my problem, my binary interaction is, let's say, analytical, and indeed I see a good convergence. If I insert the other uncertainty, let's say the indicator function, my binary interaction is no longer regular, and I expect that not a good convergence, and in fact I see. But I don't show here the calculation.
Yeah, okay. Thank you.
Okay, Michi, right? You had a question?
Yes, yes.
So, since you're using a traffic flow model, did you ever try it out on real data? Because,
Okay.
for example, like your fundamental diagram, it looks exactly like the pedestrian starters I have seen in the past, and everyone has really problems calibrating. So,
Not with this numerical approach, and not with this, let's say, second uncertain parameter, but in literature, my advisor, let's say, have compared the analytical and numerical results with this uncertainty with experimental data taken from an highway, I think in Germany, and they are in good accordance, but not with this second parameter.
Okay, there is any other question from the floor? Okay, not actually I have one. So when you're working on traffic flow model, if I remember correctly, you might end up having shock waves, right? And when you have Monte Carlo simulation, you will be able to observe these shock waves. Would you be able to observe them? And you're not able to observe them when you use a continuous Galerkin type of method. Are you able to observe them here?
Okay, I think that you can observe shock waves if you make the hydrodynamic limit. So not working on the mesoscopic Boltzmann or focal Planck equation, but working on the, let's say, macroscopic Euler of Navier-Stokes equation. So at this level, you cannot see shock wave at this level, but you can perform. If you are able to perform the macroscopic limit, the hydrodynamic limit, you can see